Okay, so hello, my name is Alejandro, and I'm going to present today the project we have been working for a year, which is how to solve stack-to-diff errors, and also present the Joule2VM pipeline in which we have been working. So I'm a researcher at the Complutense University of Madrid, and this is a project with other researchers from the Costa Group, and we are doing it in collaboration with the Solidity team. Okay, so the premise of this talk is that, in general, producing bytecode that handles the EVM stack in an efficient way is very challenging, because the EVM is very unique in its design, so not so much has been studied on how to operate at that level. So in this talk, I'm going to present the pipeline that we have been developing. First, showing why the EVM is unique and how it is different compared to other stack-based machines, and also why the stack-to-diff problem affects the EVM. From our pipeline, I'm going to explain, well, Moritz has done all the heavy work, so now that you know what the SSA is, I'm going to explain a bit how it helps designing efficient stack layouts, and also how we can generate bytecode that uses those layouts in an efficient way. The key point on the talk is that thanks to working on this SSA representation, we can repair any kind of stack-to-diff problem in any arbitrary situation. And finally, we will discuss a bit the experimental evaluation we are performing and some conclusions. So what makes the EVM different from other stack-based machines? Well, the fact that other stack-based machines also rely heavily on registers, whereas the EVM doesn't have registers. So this means that other stack-based machines, whenever they have to perform a computation, of course they use the stack. But if I need to reuse that value at any other point in the control flow graph, then I store it in a register and load it when I need it. In the case of the EVM, we have no registers, so of course I can use either the stack or the memory regions to pass the values around. And in fact, the memory becomes expensive if you use it too much. So in the end, you prefer to use the stack. This also leads to very different designs in their opcodes, because in the case of WebAssembly and the Java Virtual Machine, they are very limited in the way they use the stack. But in the case of the EVM, well, we can basically manage the first 16 elements we have, which gives a lot of freedom. But also, passing variables through the stack has their own problems. And this is what we call the stack-to-diff problem, because in the case of the EVM, if I try to retrieve a value that is beyond def 16, I cannot do it, because I have no opcode that can retrieve it. And this is not a problem of the Solidity compiler or any compiler. This is something that happens in the EVM. As an example, if we have a stack in which we have more than 16 elements, and we want to use something that is in the 17th position, while keeping all of the other variables, it doesn't matter how I organize the stack, I cannot access it, because I cannot remove the variables in between. So in this case, of course, the only left option is to use the memory. Good things about the Solidity memory layout is that it allows us to use some region of the memory as registers, so we have some kind of fix that we can do. In particular, they have this free memory pointer that points to the next free position in the memory, and what we can do is to determine how many memory positions I need for storing the intermediate values, and this is going to be my spilling region. Of course, there are some situations that we don't want to handle, which are, for instance, memory unsafe blocks or recursion. OK, so we have proposed a pipeline that is quite similar to the new pipeline that Moritz was discussing. So it's different in the way that we apply the code gen, but the general idea is more or less similar. So we initially have this Joule control flow graph in SSA form. And what we do is a bottom-up analysis to obtain this liveness information, which is the information we are going to use to determine how variables are passed through the stack. We also have other information that is going to help us designing good stack layouts, which is this distant to next use dictionary, but we don't care that much about that. So once I generate the stack layouts, which are what Moritz was saying, we have the contents of the stack at the beginning of each block and the contents of the stack at the end of each block. And using this information, together with the expressions we have to compute in each block, we can apply a code generation algorithm, which in our case differs a bit from the one that is being proposed into the Solidity compiler. So, similarly again to Moritz's idea, what happens here is that in this point I can encounter stack-to-deep problems. So what I'm going to do is to annotate them, assume that at some point I have stored those variables in some region of the memory, and then as a last step, I'm going to do an extra phase in which I'm going to repair those accesses, and also I'm going to apply some stack allocation techniques to do it in an efficient way, which is going to generate our final bytecode. Okay, so, well, how is the Joule control flow graph? We have seen other examples before. This is a bit more complex. So you can see that we have, this is a very simple case in which we have a conditional, and then we have two nested loops. And the right figure is the one that represents the control flow graph, which is a bit simplified, but this is the idea. As you can see, for instance, V1 represents the initial program point inside the function, then it jumps either to V2 and V3, and they are joined in V4, in which I have this phi function in which I decide which is the variable of the original limit variable. Okay? So again, this is in SSA because we can see that we have multiple phi functions that basically represent this conditional how to assign a variable in a conditional situation. And we have in some of the blocks, which are also like the entries of the two loops we have there. So again, the first step is to compute the liveness analysis. For this is some kind of bottom-up analysis. And the good news is that doing this analysis under SSA form is very efficient. In fact, if you do it in a non-SSA form, it is a fixed point analysis, which you can iterate a lot. But here, you can do it in two passes over the control flow graph. We also compute other information that is going to be helpful, but again, this is like more technical part. What is important is that the liveness analysis is going to give us the way to decide how to propagate information using the stacks. So for instance, in block 1, we know that the liveness analysis says that X and Y are live at the beginning and at the end, and this means that my stack has to contain both X and Y. Okay? So the next step is this stack layout generation phase. And the good thing is that as we have the liveness analysis, in the end, generating a stack layout means that I have to give an order in which they appear in the stack, so that later the code generation phase can assume that the variables are propagated in a certain way. In our case, we do it in a top-down way, and the reason why is that, well, Moritz couldn't discuss it much, but the thing is that there are many times in which we don't want to remove variables that are no longer used. Because if I remove every variable that is no longer used, this means that I have to introduce a pop instruction for each of them, which would make my code really inefficient. So that's why we introduce this concept of garbage, which is a way of saying, OK, there is an element that is no longer live, but I can just leave it at the bottom of the stack, and I can forget about it. And you can see it, for instance, in block 6, which is the block that returns the solution of the function. And you see that in the end, I have many things in the stack, but only B6 is relevant. But I don't care about the contents of the stack in this situation, so I just use it and keep it everything as it is. OK, so just give you an intuition why doing it top-down, and again, how the SSA is helping us to design these stack layouts. Initially, we know that either the stack is empty if it's at the beginning of the program, or if it is a function, then I know that in which order the function arguments are passed. So I know initially which is the inner stack of the first block, in this case, B1. So what I do in our stack layout generation algorithm is that at each point, I propagate the information so that I can I can compute the in stack of the successor blocks. And we see that in the middle control flow graph, in which you say, OK, I propagate the out stack of B1, and then B3 and B2 must have the same stack, because in the end, they are joined together. One goes after the other. So if I have those contents of the stack at the end of V1, then I have them also at the beginning of V2 and V3. The trick here, or the point on using SSA, is that the SSA makes it easier to decide how to propagate these stacks. And we see it when we want to generate the outer stack of V3. In this case, I have two blocks that jump into the same one before, so I have to ensure that before their inner stack is compatible with the other two, because they are joined together. So the way I do it is first decide how the inner stack of B4 is propagated, which in this case is like this. And then, thanks to the phi functions, we can propagate it to their predecessors and just fix the out stack of those blocks so that they are joined together. Okay? And the good thing is, again, that using SSA makes it easier to decide how to do this unification. OK, so the next step is the bytecode generation. So now we know how the contents of the stack at the beginning of the block, at the end of the block, and also I know which expressions I have to compute. OK? So what I have to do is try to use the stack efficiently to generate bytecode that produces, that computes everything that needs to be computed. So in this case, we propose a greedy algorithm that it's, again, top-down. But not only we have to do this thing of fixing the layouts in between, but we also choose in which order we want to perform the computations, because this is beneficial in the way that we can build the code. When we encounter a situation in which an element is too deep to be accessed, what we do is introduce an annotation, which is called the virtual get. That just says, OK, at this point, I have to retrieve it from memory. I'll solve it in a later step. In our previous example, if we assume that the maximum stack depth I can access is 4, then I would have these two begets that represent that those ones must go through the memory. OK, so how the greedy algorithm works is that it is an iterative algorithm that chooses an action at each point that transforms the inner stack into the outer stack. And these actions can be either popping the topmost element if it is not used elsewhere. We can place a variable in their corresponding position in the final stack, and this is done in terms of the bottom of the stack, because once placed in that position, it does not need to be moved elsewhere. Or the most common one is just choosing the next computation to perform. Okay? And when there are no computations chosen, I have computed everything, so the stack I have is a permutation of the one I want to achieve. So if I have to do some other changes, I do it at that stage. OK, so now we go into the more technical part, which is how I repair these unreachable accesses. So the idea here, as I said, is that in the previous phase, we have marked with virtual gets all the places in which I need to retrieve a variable from the memory. And in fact, what I want to do is to replace this virtual get with a push to the memory address in which I have that variable, and then do an mload to just load it. OK? So the key idea on doing it in a general, efficient way is that everything we have done so far is preserving this SSA form. So this means that we have access to existing techniques that use the SSA form for propagating the variables using registers. In our case, it's the memory, but in practice, we are using it similarly to registers. Okay? But to apply these techniques, there are two things that we have to do. The first one is to identify which phi functions are involved, and I'll give you an intuition on why phi functions in particular are relevant in this context. And then I have to decide where I introduce them store. So if I, for instance, before had the bget for variable b2, then I also have to do at some point an store that stores it in the corresponding memory region. Okay, so the first part is identifying phi functions. So here the idea is that for every computation that we do usually, we know that it appears at the top of the stack. So I know that there is a point in which I can duplicate it and store it in memory. This strategy preserves all the layouts I had so far, so I'm not breaking anything. But also, yeah, this is the way to go. For very simple cases, it works. The problems are phi functions, and what happens with phi functions is that as they are like basically saying, okay, combine these variables, they might not appear at the top of the stack, and they might be even very deep to be accessed. So I cannot just duplicate it and store in memory. So this is another example in which we have to virtual get two variables defined by phi functions. And in this case, what I'm going to show you later is that solving this v5 and v6 also triggers other variables to be passed through the registers. Okay? Then, once I know everything that must go into registers, I have to decide when or where, in which program point they are stored. So of course, I could just store them when they are computed. But again, as we have the stack layouts that preserve all the information that we had so far, it is better to do it in a lower point, because this allows us to reuse more registers and not to use so much memory. Okay? Again, this is very technical, but just to give you an intuition. So we decide where things are stored, and again, we can do this in an efficient way thanks to the SSA. In a non-SSA setting, this is not that easy, because I have to decide where to store all variables in, well, you would like to have it in just one pass, and this is thanks to the SSA. So this would be the code that would be generated. As you can see, handling phi functions can affect different blocks and different variables. In fact, variables v1, v2, and v4 must be duplicated and stored, whereas in the initial setting, we don't have this. But again, the idea here I want to emphasize is that this works for any situation. So because we are working with phi functions, it doesn't matter how complex our control flow graph is. We can do this trick, and we can solve it in just linear passes. So this is basically the whole pipeline that we have developed. Okay. Going back to the initial example, how do we replace these virtual get annotations by actual code? So as I said before, we can use memory address 80, which is the first one that is available to use in the Solidity layout. And I just load the variable from that region. And in block 4, what I do is to store v2 in memory using amstore. Okay? And this is the two extra passes that I have explained before. Okay, so now I'm going to discuss a bit about the implementation and the experimental evaluation. So this has been implemented as an independent tool from the Solc compiler, because the code generation algorithm was already part of another implementation, and that's also why we have it in Python, but it is available online. So I'm going to present the results for two evaluation datasets. The first one is the Solidity benchmark set, which explores different situations, and of course we are passing it with our pipeline. And the second one are they are 16 contracts that we have downloaded from SourceFight that are producing stack-to-deep errors in the latest Solc version. As you may imagine, people doesn't publish contracts with a stack-to-deep, so it is very difficult to find the situations in which we can apply our pipeline. So for benchmark A, we are achieving savings in number of instructions, the number of bytes, and an estimation on the total gas. And this is because we are doing moving things in a better way. So that's why we are showing like all the different parameters for a fair comparison. In the case of benchmark B, we are repairing all the stack to deep cases, okay? But as they were at some point, they could, the Solc compiler at some point could generate code. They are mild stack to deep errors. They are not so complex. So what we said was like, okay, let's take again the first benchmark, and we're gonna say that instead of being able to access position 16, now we can only access till position 8. And suddenly, of course, we have a lot of stack to deep errors. So we tried with again with the benchmark A, and we solved all this stack to deep. Of course, the code is worse in this case, but because we don't have that much freedom to manage the stack in an efficient way. A bit of the experimental evaluation. Again, consider that we are working in Python, so our tool, of course, is going to be a bit slower, but not that much. And what is interesting is the graph on the right, in which we show the times for the different phases in our layout generation. And what we see is that right now, what is taking the longest is the control flow graph generation done by the Solidity compiler, which seems to indicate that, yeah, the analysis we are doing, the layout generation and grid repair, in the end are linear passes. There are multiple of them, but they are linear, so they behave quite well when the code grows. Okay, so in this, just to conclude, in this talk, I have presented the pipeline of the grid tool, in which we are generating EVM bytecode from the Joule control flow graph SSA representation. It is quite similar to the ideas Moritz has said, but like we are using a different code gen that is like more flexible for some things. And the good thing is that we are addressing this stack to deep problem in an efficient way for general cases. So this project has been ongoing for a bit more than a year. So we have been discussing on the best way to do to exchange format between the Joule control flow graph representation from the Solc compiler, and also we have done a lot of debugging together with them, because in the end, having a stable version that works, that passes all the tests, shows a lot of bugs to fix. And one of the main limitations that we are having so far is that this Joule control flow graph that is generated from the compiler is missing some optimization passes, because these optimization passes are being done at the level of the EVM bytecode in the compiler, so we don't have access to them. And the ones that are more relevant are the function inlining and also some redundant cut elimination that make it quite difficult to compare block to block with their pipeline. So this hopefully at some point is going to be improved, so that we can apply our pipeline like as a last step in the generation phase. So for the future, we have several ideas. We want to, so our fix now preserves all the stack layouts, but we would also like to remove variables from the stack layout so that we can solve some collateral stack to dips. And this is something that we are working on, that having this kind of stack pressure and deciding to just, from the beginning, move it to the memory. We don't want to use it in the stack. We also want to improve the heuristics for handling garbage, because this is, I think, one of the most crucial parts on generating good bytecode, a good way to handle this garbage. And finally, we also are exploring better ways to do the greedy algorithm, and in particular, we want to find better ways to choose the order in which we perform these computations. So that would be all. Thank you. So now the tool is available online. We have to document it because so far we have been working on having it stable, but just if you want to see it. Thank you.
Thank you so much, Alejandro. We have quite a few questions already, so I will be delivering the questions to you. The first one is, why don't we make use of transient variables instead of memory to solve the stack to deep problem?
Why don't we, sorry?
Why don't we make use of transient variables instead of memory?
So memory, I refer the normal memory that it's like the cheapest one. So I think the transient storage doesn't make sense to use because it's more expensive to use, so we prefer to use it just the memory. We don't need to do more complex things.
Okay. And someone also asked that shouldn't this memory deduplication strategy make the code more expensive?
So,
Why are we seeing gas saving in the benchmark?
so the thing is that the stack layout generation thing preserves the variables in the same order, so we don't have to be swapping things around. So most of these savings come because we're trying to do it. So maybe I haven't given much emphasis there, but what we try to do with the stack layout generation phase as an isolated phase is to have stack layouts that don't move things around. So we are achieving savings because we are not moving things around. Even if the stack to deep errors occur, we are being very careful to avoid them as much as possible, and this is why we are having some gains compared to the VIR pipeline now.
Awesome. Another question. Can you expand on what optimization metric is used to select which variable will be moved to the memory?
So far, well, that is part of the. So far, the only variables that we are moving to memory are those ones that produce some kind of stack to deep errors. So if I understand it, this means part of the related work we want to do. And for that, probably we'll have, so in SSA, or in already existing techniques for SSA in registers, there is this notion of pressure, and there are metrics based on how many on how many registers I'm using them too much, and we would have something similar to that idea. Okay, but we still have to explore it in more detail. So the idea would be like to choose those variables that if I just pass it only through memory, then other variables are freed as a result. So they don't have stack to diff problems.
Okay. Could we make variables share stack slots?
Sorry?
Could we make the variables share stack slots?
Yes, stack
Share the stack slots, like 2 uint 128 or 4 uint 64 variables. Can we make them share the slots?
to share slots for what? Sorry, I don't
Um,
understand the.
Anyone who asked the question, do you want to elaborate on the question? Any takers for this question, please? If not, then we can also.
Okay.
It's not my question, but I can explain the idea. Is
Okay.
that in storage, we usually put multiple values to the same slot because slots are so expensive. And given that Slack slots are just words of 32 bytes, I'm guessing the question is whether it would make sense to put multiple variables that are smaller than 32 bytes together in the same location.
I think it could make sense, but it's a different thing. Well, it's a difficult thing to do in a good way. But the good thing is that when you do the stack allocation techniques, you have like all the freedom to choose the way in which you store things together. So if you detected some kind of situation in which that would be viable, you could do it. But for now, we haven't explored it because we understand that's quite difficult now to manage. We assume like every variable has their own, is stored independently in their own address, and that's all. But of course, that would be a nice thing to consider, yeah. Thank you.
Okay, one last question. Would it not be preferable to duplicate or swap a value before it gets too deep instead of using memory?
The thing with, yeah, in general, you would like to do that, but the thing we are doing in the stack layout generation phase is that we try to avoid these situations directly because we construct the stack layouts in a way that everything that is going to be used soon appears on the top. So we can do some kind of tricks to address this part, and in fact, we are doing them. But this is done like at the level of the stack layout generation phase, not at the level of the bytecode generation. So in the end, the stack layout generation phase, there are very specific properties that your layouts have to verify, so you can work following that idea. Yeah. So we are doing some tricks there to make things appear again at the top, or by designing in a top-down way these stack layouts.
Thank you so much, Alejandro. That will be your time.
Thank you.